Okay? Apoptosis is the creation of these little blebs. Okay. Okay, but, and so everything remains bound within a membrane. And then that membrane is relying on macrophages to pick up the apoptotic body. So there has to be a way to attract the macrophages to the apoptotic body. Got it? Okay, so what we see happening in apoptosis, okay, so this is outside the cell, and this is inside. This is the plasma membrane. One of the phospholipids, I'm just going to do that, phosphatidylserine, is almost always at the bottom, on the inside of the cell. It's one of those phospholipids that has an overall negative charge because it has two negative charges and only one positive charge in its structure. So it's one of those, we talked about the fact that there's an abundance of negatively charged phospholipids on the inside of the cell. Okay? During apoptosis, and this is an energy-driven process, so if you get the apoptotic signal, okay, the phosphatidylserine flips to the outside layer of the cell. I'm going to put a little minus in there. Okay, so phosphatidylserine moves to the outside of the cell. And this is what attracts the macrophages to the apoptotic bodies, is the abundance of phosphatidylserine on the outside of the cell. There's probably other markers too, but this is one way that macrophages don't eat you eat your alive cells, but they tend to eat apoptotic bodies. Okay, so there is an assay, a lot of you are going to see an apoptotic assay that actually looks at the movement of phosphatidylserine from inside of the cell to outside of the cell. It's an extremely common apoptotic assay. So there's a protein called annexin that binds to phosphatidylserine if it's on the outside of the cell, because as a protein it can't get into the cell, so it can only bind to phosphatidylserines that happen to be on the outside of the cell. Okay, now you can't really see annexin bound to a cell. However, if you put a fluorescent dye on annexin, now you have a way of marking cells that are apoptotic. So the more fluorescent a cell is, the farther along in the apoptotic pathway it is. If the cell doesn't fluoresce much at all, it's a pretty normal cell. Okay? So what we're going to do is measure the fluorescent intensity of cells to see how much annexin was able to bind in that cell. Okay? So we got to look at, well, how do you measure the fluorescent intensity of a cell? Okay. Well, you have to have a flow cell cytometer. And DMU has one that I've used, but now they haven't used it for a while, and because I asked to see if I could use it for the biochem lab and bring biochem students up there to use it, but apparently not, because nobody's there to use it anymore. Okay, so the flow cell cytometer drops cells one by one through the, you know, kind of through a little chute, well, or tunnel kind of thing. Okay, so each one of my circles is an individual cell. And in order to pick up the fluorescence, as a cell kind of floats through or drops through a detector system, a detector is shining a light on the cell. Okay, a light that would excite the fluorescent dye. Okay, so fluorescence is different than luminescence. You have to excite the dye in order for it to fluoresce. Okay, so as this cell is passing through that light path, okay, it gets excited, or the fluorescent dye gets excited, and the cell will fluoresce. And then that's picked up by a detector. So you can sit there at the machine, and that's really pretty much all you do is sit there and read a book, while the machine is maybe counting in 5 minutes about the fluorescence of maybe 12,000 cells. It's really fast. And think about sample numbers. That's pretty cool. You have a sample number of about 12,000. Pretty good statistics there. Okay, so once you're done, you have to, a computer program will say, okay, everything here, and then it puts a dot on it graphs each dot in terms of where they are or how fluorescent they are. And it picks a window that says everything down here is, the cells are alive. If you start seeing a lot of fluorescent intensity, the cells are apoptotic because we're seeing too much fluorescence. There's a lot of annexin binding to these cells. Okay, so there's a computer program that decides where that line is. You can manipulate it, and I was never really good at that, but you can manipulate it. Okay? So that's what's one assay, is just how much annexin is bound to the cell. A lot of people aren't satisfied with that. And I'll tell you, I'll explain, well, I can explain that. And that's because if a cell is committing necrosis, okay, and it has holes punched in the membrane, annexin will get into through those holes and bind here, okay? And then the researchers don't know, okay, did this cell die by apoptosis, or are we seeing necrosis? Because you punch holes in the membrane, annexin gets in, binds to the phosphatidylserine on the inside of the cell, and then we really found out nothing except the cell's dying or dead. Okay, but there's a solution to that problem. Okay, but do you understand why this can't distinguish between apoptosis and necrosis? Okay, does that make sense? Okay, well, here's the solution to the problem. We're going to do another dye, fluorescent dye. And even though the DNA is chewed up, it's still there. It's still there. Okay? And the dye is called propidium iodide. Okay, it's fluorescent, a different color fluorescence than the dye they put on annexin. But it's only fluorescent if it binds to DNAs. Well, it's fluorescent if it does. It's just that you can distinguish between DNA-bound propidium and non-DNA-bound propidium. But propidium iodide cannot get through the cell membrane. It doesn't fit through the cell membrane. It gets too charged. It has to be charged. Okay? But propylium iodine, it can sneak through the holes in the membrane that you would find in a necrotic cell. So how do you distinguish between apoptotic cells and necrotic cells in terms of just propylium iodine? Which ones are going to be more fluorescent? Yeah, the ones that commit apoptosis, or the ones that are dying by necrosis. So, when the cell, when the light is going through, actually the cell is going to be excited by two wavelengths, one to excite this dye and one to excite propylium iodide. So you give us the cell, in the cell assay, you add a Nexen to the cells, you add propylium iodide to the cells. Okay? Then as the cells are passing one at a time through the flow cell cytometer, two lights are being used to excite the cell. So this would be for the Nexen. Okay? And then the y-axis is also fluorescent intensity. But it's the fluorescence of the propylium iodide. Okay, so so one's probably a red color, one probably this is probably orange. So we probably have a green and an orange or something like that. Okay, and then the same thing. They at the end of the program, after you've gotten about 9,000 to 12,000 cells through, the computer program says anything down here is pretty normal. Okay, so these are alive. And these guys are dead.
But they would be necrotic.
Yeah, yeah. Okay, so if you have one of these assays, you're going to see a graph with a whole bunch of dots. Each dot represents the outcome of for a particular cell. What's its Nexen fluorescent activity and what's its propylium iodide fluorescent activity? And what can we say about all of the cells in this block? Yeah, these are alive. Okay, what can you say about the cells in this block?
They're either apoptotic or necrotic.
No, go back.
Just like
They have low PI fluorescence, so these are apoptotic. Okay, so you see a shift, and sometimes you really see a shift towards these, and these would be,
because they have both.
Maybe both.
you could say they're necrotic, and there's some argument about how to interpret this data actually. So most people are looking at the shift here. But we could say necrotic. Some people sometimes say, well, those are late apoptotic. So those belong in a category that different investigators or different authors have different takes on what's in that box. Okay, but I'm pretty sure some of you are going to see an Nexen binding assay if you're studying apoptosis. And they're going to not only look at a Nexen binding, but PI, propylium iodide fluorescence. Okay, I guarantee you some of you will see that. In fact, there's a lot of just really cool assays. DNA fragmentation, I saw a paper just recently just showing the DNA fragmentation on a gel. I'm not sure I accidentally chose it, but you might be seeing that. Okay, any questions about that? I hope some of you just, I understand the paper. Okay, so in the last 10 minutes, okay, I wanted to talk about the overview of apoptosis. Okay, so whether or not a cell will commit apoptosis is dependent on the activation of, these are protein digesting enzymes. Okay, that sort of kind of begins to degrade and eat up the cell so that it can shrink and you're not spewing garbage. Okay, procasphases are almost all shaped alike. So that's going to be my procaspase. From now on, that's procaspase activity. And in order to activate a procaspase, you cut out a middle chunk of the amino acids. And you end up with actually the caspase being made up of 2 protein fragments. There used to be 1. Okay, so now there's 2 proteins. So you cut out a middle piece of protein from a procaspase, and you end up with the procaspase being made up of 2 peptides that used to be part of 1 protein. I don't know of an apoptotic pathway that does not include caspases, okay? And we'll talk about different caspases later, but that's the overview. You've got to activate the caspases if you're going to commit apoptosis. And of course, there's a war going on in the cell. Okay, so here's the cell. Okay, and the war gets really, most of the war is happening actually at the mitochondria. But this is sort of an overview of what's going on. Okay, so there are going to be forces that block apoptosis. Okay, these are sort of stay alive signals. There are going to be forces, okay, that say commit apoptosis. Okay, and some of these commit apoptosis signals are coming from inside the cell. Some of them are coming from outside the cell. Okay. So there are death signals. Death receptors. This would be a good Star Wars. Okay, and then there are survival signals. I should do survival signals on okay, so even signals from a different cell will say stay alive, don't die now, really kind of need you. And there are some cells that will say you're really posing a danger to the entire organism. Please commit apoptosis. So we'll take a look at a couple death signals. One is we're going to look at the Fas ligand, also known as CD, no, 95, L for lung. And the receptor would be CD95. Did you talk about that in immunology by any chance? Just a little bit? Okay, we're going to be talking about that. On the cytotoxic T cells? Yeah, because those are the presenters. I think a lot of the cells that are expressing Fas ligand are cytotoxic T cells. So a cytotoxic T cell will tell an abnormal cell, commit apoptosis, for heaven's sakes. I mean, there are other contacts that are important too. Tumor necrosis factors. And they all function basically the same way. Okay, so we're going to look at Fas ligand and how that kind of signal that is sent. The tumor necrosis factor is going to activate very, very similar proteins, do the same jobs except they have different names. Okay, survival signals are in a lot of tissues. It's really important, like the lining of the small intestines, for example. You don't want a whole bunch of cells to just willy-nilly commit necrosis, because then you lose the lining of the intestines. Okay, so sometimes for tissue integrity, when two cells that are just alike touch each other, they're giving each other survival signals, so you can maintain the integrity of that tissue. But there's like nerve growth factors would be don't die now, for heaven's sakes, is a survival signal. Contact with another cell, like cell, contact with another like cell. So kidney cells will keep other kidney cells alive, but they really don't have any influence on a liver cell. A liver cell and a kidney cell probably wouldn't survive because they're not the same. Insulin-like growth factor. Okay, so we won't really be covering survival signals, but they're going to do the opposite of a cell death signal. Okay, cell stresses are internal. Okay, so we'll be thinking in terms of what triggers apoptosis as extrinsic signaling and intrinsic signaling. So let me put that. The pathways are a little different, although they overlap so much that it's not going to be a huge deal for us to distinguish between extrinsically triggered apoptosis and intrinsically triggered apoptosis. But there's assays to determine whether apoptosis is by intrinsic factors or extrinsic factors. We won't get too bogged down into that. DNA damage is certainly going to trigger apoptosis. Okay? So too much DNA damage, the cell's going to commit apoptosis regardless of what kind of survival signals it gets or what kind of death signals. It's just now just paying attention to the internal signal to commit apoptosis. Oxidative stress, too much. Oh, this is a good paper. I have to look for it. And I got 2 minutes. Okay, let me get down the other thing I have. ER stress. Yeah, because we'll come back to ER stress. Okay, let me go back to oxidative stress. Because you could, I saw 2 papers last year on oxidative stress. So sometimes somebody having a stroke or like a heart attack, that causes the loss, both of those might cause the loss of flow to some parts of the brain. Okay? And so that part becomes, well, you could say ischemic or hypoxic. So one tendency was what people used to do was, oh my gosh, put this person on oxygen. Okay, so the person starts breathing oxygen-rich air, and that return of too much oxygen causes apoptosis. Okay, so the person went through a period of hypoxia, and then that's followed by reperfusion. Is, well, let's get that oxygen back to the cells. And there's such a flood of oxygen back to the cells that it causes oxidative stress and apoptosis. So one way to stop that from happening, the apoptosis after reperfusion, is to supercool the body. Can you imagine? So they put the person in an induced coma, because I can't even imagine. And then they just lay the body's on a bed that circulates cold water, and then they cool the body. Yeah, the cold water's going through the tube, it's not, there's no point in the body. It's just going I think they can get the temperature down to about 85. Oh! And that prevents a lot of the apoptotic, the apoptosis in response to reperfusion. So if anybody wants to do a paper on reperfusion injury, so one time one of my students' father was on one of those hyperthermia beds, and I asked Adam, I know this is illegal for you to do this, but can you find out if he's okay? And Adam said, I don't have, and I told Adam the guy's name, and he said, you don't have to tell me the name, because there's only one, at that time, there's only one bed at Mercy that would allow you to lower, induce hypothermia.